So to understand the first probabilistic kind of model, transition kind of model, we'll be using a book, your example from your textbook, which is really a grid word of a small word, in other words, consists of these cells. It's a 4x3 word, and this cell here is blocked, so you cannot really transition into that kind of cell. And this grid word is a stochastic environment. It starts, if you like, from the goal of the agent, that always starts in this kind of location, is to maximize, to move, if you like, into a goal state. And there are two terminal states here. One is that will offer a reward of +1, another with a reward of -1, in a kind of an optimal way, in a sense that it will try to maximize the reward, at the end of that game, which in this case is it's not really a game, it's just basically a small word, is reaching this terminating state with a maximum possible reward. All right, the environment is stochastic in a sense that despite the fact that the agent is intending, let's say, to go north, then the agent can end up in any of the other states, so it cannot move outside of the wall, so it will bounce back onto this wall, and it will go north with probability of 0.8, but it will actually go into this state S21 with probability 10%, and it will bump against the wall and remain on that kind of state that started S11 with another 10% probability. Okay, so this is the sort of word that we are going to use in order for us to build, if you like, an understanding about what is really the transition, the probabilistic kind of transition model we have kind of talked about over here. So I forgot also to mention that there is, if you like, a penalty of minus 0.04 if we just endlessly move into non-terminating state. So all of the cells that you see here without numbers, they do contain the minus 0.04 reward. Okay, so this reward is negative, slightly negative, a very small number, because it will lead to selecting at the end of the day policies that are not going to, if it was positive, it would actually mean that the agent could over time gain far more than one reward by just endlessly moving in that kind of inside that kind of environment. So with the minus 0.04, we avoid kind of reaching this type of policies. So intuitively, we can actually understand what will be the best trajectory to reach, if you like, a good terminating kind of state. Let's say this state over here, the state S43. Obviously, it is really this trajectory over here to go north and then to go east to reach this trajectory, to reach this terminating kind of state. And the reason why it is this and not, for example, this one, is that while it is actually moving around here, given the stochastic nature of the environment, despite the fact, as we discussed, to intending to go north, it may end up into the -1 terminating kind of state, and therefore kind of lose, in quotes, if you like, the game. So we have 11 states, and therefore we're able to define sort of this type of matrices. And I'm going to have a matrix of an 11 by 11 kind of matrix. So okay, it's not really to scale here, but this is basically an S11 state all the way to S43, and this is, let's say, the current state axis, and the other state, the other axis is the so-called S prime, and the S prime axis is also S11 to S43. So the matrix is effectively giving us here, it has some kind of tabular form of the underlying transition probabilistic model. So we know that conditional probabilities can be fully specified by matrices. So the P of S prime given S comma A. So we need to have one axis assigned to the initial state, another axis associated with the S prime. So we are missing the A, and so therefore we can define one of those matrices for the action north. Okay, it is also in the, I think in the textbook, it is actually not really north but up. Then the second matrix will be exactly of the same notation, will be for down, and the third one for right, and the fourth one for, I'm not going to even draw it, for left. Okay, so four matrices. With four matrices we have fully specified the probabilistic transition model. And so let's put some kind of numbers down. From S11 to remain to S11, this can happen with probability 0.1. From S11 to move into the another one to S12, for example, this will be with probability 0.8 according to the transition model that we have introduced, the stochastic environment. And then finally we will see at some point S13, and then S21 will start to be specified. In the S21, this will be 0.1 here. So the summation of the probabilities of all the possible S prime states will be equal to 1.0. So all rows will actually sum to 1.0, as we might expect. And the same thing can be specified for all other three matrices. And that's how we end up with something that it is effectively a computable transition model. For this specific small dual, of course, is trivial. And we are able to just use these transition probabilities. Now we'll see how we are going to be using to come up with optimal strategies on how to move in this kind of block world optimally. We had defined earlier as part of the MDP dynamics a second component of MDP dynamics, which has to do with the probability distribution of rewards, again conditional on the state and the action we are actually taken. And what we will do now next is we will use this probability distribution and more specifically take a statistic out of it, which is the expectation, and we will to define what we call an expected reward, also known as a reward function. So this is symbolized in some instances as R of SA, also in some textbooks as the function R that has arguments, the state that we were and the action that we have taken. Okay, and this actually is an expectation, operation. Expectation over the RT at time instant t, the reward at time instant t, given that we were in st minus 1 is equal to s, and took an action at minus 1 is equal to a. And let me write it down, is the expected reward received after we execute action A from state S. Obviously, R, the reward that we will be accumulating, is going to be a function of the next state, which is we are going to end up. Evidently, the next state is a stochastic state. And then, of course, that state will actually have a specific reward associated with another action will be taken to end up in an S double prime state, and so on, in all subsequent states. And so this expectation is over the reward. And this actually can be written as summation over R that belongs to the set of rewards calligraphic R R summation of S prime being in S, P of S prime comma R given S comma A. And of course, this thing over here comes from the definition of the expectation operation, which is defined here as the expected value, let's say, of a random variable, let's say x, is some summation of x, p of x. And also it's worthwhile, and you see it in, we'll use it as well. In many instances, we have a reward function, which is now has 3 arguments. So this is the S, A, S prime. And this is an expectation of RT given ST minus 1 is equal to S, as you expect. ST minus 1 is equal to A, and ST is equal to S prime. And this will actually be given as an expectation. This expectation is can be written as summation of the joint of R. This for R belongs to the set of rewards. And then over here we have a ratio of the associated kind of conditional. So we will write the conditional as in usual way as the joint S prime comma R given S comma A divided by P of S prime given S comma A. So the first term here we understand it from the definition of an expectation operation. The second term is a conditional over here that involves the S prime. So effectively the conditional will be the joint divided by the marginal of S prime. And that's basically how we ended up with this kind of expression for the reward function. So we have 2 reward functions. One is, or the other is going to be used for sort of defining, if you like, what is happening in terms of the solution that we are going to come after. All right, so now that we talk about rewards, the goal of, we can actually write that the goal of the agent is to maximize. This will actually give us also the pretext to write down some expression about this very specific goal. The goal of the agent is to maximize the expected, the total, let me count the total amount of reward it receives, period. Okay, it receives. That's basically the goal. And now, evidently, this does not mean maximize the immediate reward, but maximize a cumulative reward over the long term, over the long run. Okay, so that's basically the goal, and we'll actually need to define now a quantity that we will be calling a return, that it will have elements of what we just wrote down here. So the return is given by an expression. We will call it GT. Is the cumulative discounted reward that we can actually get starting from state ST. So the discount, we will explain now what the gamma factor is doing here. This is, it could go forever, or it will terminate at the specific terminating kind of state. So from t is equal to 0 to infinity, let me write down the expression for the former part, gamma k RT plus k. So this is the sort of infinite, what we call infinite horizon problem. Return. And when we say about infinite horizon, we don't mean that the interaction will last for an infinite amount of time, but what we mean that we do not impose a specific deadline to the MDP problem. All right, so evidently that fact, if we do impose deadlines, the strategy and the associated, in other words, policy will actually be quite different. Remember what happens in a basketball game and the complete change of strategy for a team that has only, let's say, 10 seconds to finish the game. And let's say the difference is, let's say, 2 points, and the losing kind of team completely changes the strategy on those last 10 seconds of the game, trying to score as much as they can and win the game. Otherwise, the previous strategy is basically no longer applicable. So that is an example of, from real life, of something that has now a deadline, and how this affects the strategy. With respect to the discount factor over here, you can understand that when gamma is equal to 0, then effectively we have GT is equal to RT plus 1. So effectively, we have absolutely no incentive to look beyond the immediate reward as far as the agent is concerned. When the gamma is something which is very close to 1, then what we have here is we have a GT that it is going to offer long-term incentive to the agent. And when we have a gamma which is greater than 0, but a small number, then we can adjust on by gamma on how long or short term we can be. Varying long and short and long term incentive. So the choice of gamma is a kind of considered to be a hyperparameter in this kind of MDP problem definition. Is one of those parameters, if you like, of the problem. And therefore it plays kind of an important role on the selected strategy at the end, as that example sort of I gave you indicated. All right, so now that we have seen the return and kind of make it kind of connect that to the long-term goal of the agent, I think it's going to the time has come to define a very important, formally, a very important term, which is called policy. So what is a policy? Is a mapping from state to action. And in fact, when we typically talk about policies, we are defining, if you like, an action for all possible states that we have in the problem, or at least the ones that we are visiting. And as we'll see later, this distinguishes also exactly how many states we are visiting, would distinguish also the definition of the various algorithms that we are going to be involving to solve the MDP problem. Right now we are at the definition kind of stage. So we have effectively two types of policies. We have the so-called deterministic policy, and we have a random or stochastic So in both instances can be accommodated by treating effectively this pi as a probability distribution. So we can actually write pi, so pi is going to be the symbol for our policy, and we can define it as something that has the action that we are taking given the state that we are in. And this should be interpreted as a probability over all possible actions. So we can have, let's say, A0 given S, P of A1 given S, let's say P of a cardinality set of A given S. And in the case of deterministic policy, if you are in S, you will actually have one of the terms being 1 and all the others are 0. In the case of stochastic policy, you have all the elements effectively being non-zero. Okay, obviously the summation of these elements will actually equal to 1.0. Okay, so that's basically the the definition of a policy. It will define for us, this is basically what we're after. We are going to find the optimal policy to that it will effectively allow us to do the following. For every state that the agent will be able to be in, we will be able to draw an action, let's say up, 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 right, right, and we are in terminating state over here. Obviously, in every cell, in every of these states, we may be able to have more than one action as the optimal, and so therefore we need to continue to. But another important thing is that we need to define all of the for all states, all of the actions. So this policy effectively will need to be specified globally for all the states we are in.